And let's start to do a share screen. Lecture number 23. All right. So a quick recap. So last time we discussed the gauge theory. You with me? And I introduced to you the whale idea, saying how to make. Can you hear me? There's some noise. Can you hear me, guys?
Yes.
Go ahead.
There's somebody is making an irrelevant noise, or there's some noise in your general area, then please close your mic. But of course, open it to ask questions. Okay, so we discussed Whale's idea of a gauge symmetry or local gauge invariance. Right? Spoke about recap. To organize the place here a little bit better. Spoke about local gauge invariance. And I gave you the example, right, that, you know, if we take a psi of x, right, and transform it as psi prime of x times eiq, some function of x, psi of x, right, then if we want the invariance of the Lagrangian, of course, the Lagrangian directly is not going to be invariant. The Lagrangians go to L prime, which is just L minus Q psi bar gamma mu d mu chi psi. So there is this extra term in the Lagrangian. But as Whale very nicely noted, we can make the Lagrangian invariant again if we are changing the covariant derivative, right? L Dirac is psi bar I gamma mu d mu minus m psi. So if we change the derivative to a covariant derivative, namely we're adding a field to the derivative, and we require a certain transformation of the field, right? A mu goes to A mu prime, which is A mu minus d mu chi. Then the new Lagrangian is again invariant under local gauge transformation, right? But then the new Lagrangian now includes a new term. L is now psi bar I gamma mu d mu minus m psi minus this new term Q psi bar gamma mu a mu psi. We change the Lagrangian. Right. Now this new term is identified as a term that, you know, it's an interaction term between the field psi and the new field A mu, which we identify as the photon field, right? So this A mu, this is the gauge field, which we identify as a photon. Because it fulfills all the condition we have from a photon, right? So that's sort of a coincidence. It's not a coincidence, of course. It has everything we need from a photon. And then the entire quantum electrodynamic is, you know, we have the free particle plus the interaction term. And they all follow from this gauge invariance. So it's a very nice and very strong you know, mathematical insight by Weyl to show that. And if you want to write the full Lagrangian, write the LQED, we have to have the free particle term, I gamma mu d mu minus m. And then we have the interaction term. And then we have the additional free field kinetic term, minus 1/4 f mu nu, f mu nu. So that's the kinetic term for a free photon. That's the free particle kinetic term. That's the interaction term. Now, very nicely, you can see that this prescription also requires that the photon be massless, because if there was a mass for the photon, then it would destroy the symmetry of the Lagrangian, so it would not work. So again, is this a coincidence? We don't know, but it turns out that it gives an excellent description of the interaction that we see. And remember, any physical theory, the goal is to explain the experiment, and that's what it does. Is there anything beyond here? Well, I don't know. All right, questions. So, no questions?
In QED, there is no direct interaction between two fermions, right?
Right. The mediator of the interaction is the photon.
And photons also don't interact with each other.
No, they don't. Well, there is something which I may ask you in homework, right? You can think of an interaction of photons. There is this thing, I don't remember the exact name right now, I just slipped it. But you can think of a photons that do interact with each other by exchanging of fermions between them. Okay, so what I want to do now is sort of repeating what we did, but slight modification, and that's writing down the QCD Lagrangian. So QCD stands for quantum chromodynamics. And very nicely, the structure is going to be identical, nearly, to the structure of quantum electrodynamics. The difference is the symmetry. In QED, right, the symmetry group was a U1, what we said, right? This was just a local gauge symmetry, which really corresponds to a phase. Now in QCD is a quantum field theory for the strong interaction. And now the symmetry is not the U1, it's a slightly more complicated symmetry. It's called the SU3. Right, SU3 local phase transformation, local, well, yeah, I can say local gauge, but local phase transformation is enough. Now, SU3 means special unitary. So it's a group of 3 by 3 unitary matrices. SU3, we mean 3 by 3 unitary matrices. Namely, U dagger U is I, right? With determinant of 1, that's a special. Right. Now, the key difference we're going to find is that the SU3 group is a non-abelian group. Non-abelian means that the group members do not commute with each other. This is a non-abelian. Group means that the matrices representing the group members do not commute with each other. Right? Now, although it's a different symmetry, there is a full analogy with what we did in QED, right? The differences are the symmetry group and of course the coupling constant, which is going to be different. But you know, that's one of the things that make this gauge symmetry to be such a strong principle in modern physics. Now, in QED, there is a single charge, right? This is the electron charge. In QCD, we have three color charges, right? R, G, and B. How does it going to work? We're actually going to prove it right now, right? So we write down the free particle Dirac-Lagrangian for one of the quark flavors. But then we have to remember that each quark appears in the Lagrangian for 3 times. So we have, psi bar gamma I gamma mu d mu minus m psi. Now it's going to turn out to be sum over the 3 colors, or G and B, of psi bar with the given color, I gamma mu d mu minus m. The mass is independent on the color, psi for color. Right, the same mass for all different colors. Now, rather than doing all that, then we just group them all together with a simple notation. So we write down psi now as psi r, psi g, and psi b. Then of course psi bar is just psi bar r, psi bar g, and psi bar b. And use a compact notation, or GB. Let's see, I have a typo. I need to modify my typos. And so we get back to the Lagrangian of psi bar I gamma mu d mu minus m psi. But now this is just a compact notation. So compactify the notation.
Each of the psi R, RGB, are they numbers, vectors, matrices? What are they?
Functions. These are wave functions, right?
But are they scalar functions or vector functions?
Well, these are the fermions, right? So these spin half fermion, right?
So are they the same 4-component spinners we had for electromagnetism?
Yeah, of course, right? Remember, the strong force connects quarks, right? Particles that obey the strong force. These are all fermions. Right? Same as with, these are all fermions, right? That interact via the strong force, right? So these are quarks, really.
So for the spin half fermions,
yeah,
electrons and positive and anti-electrons, we had a 4-component spinners. That's the size.
Right.
Are these quarks going to be similar 4 components, or?
Yeah, similar. They are not leptons because leptons do not interact via the weak interaction, via the strong interaction. Oh, sorry. Okay. Now, but now we want to look at the symmetry group. We said that as opposed to the electromagnetism, we have SU3 symmetry group, right? SU3 symmetry group means that this is described by 3x3 matrices. So a general 3x3 matrix, right? U It's just, U11, U12, U13, U21, U22, U23, U31, U32, and U33. It's the most general way to write a 3x3 matrix, right? Each of the Uij is a complex number. Right? Right, so we have total of 18 free parameters, right? But we know this matrix is unitary, right? So U dagger U is equal to 1. So this gives us 9 constraints. Right? Which means that any general matrix U, which fulfills this symmetry, can be written or expanded in terms of 9 linearly independent 3x3 matrices. Right? So each matrix U, or the matrix space U, can be written in terms of linear combination of 9 3x3 independent. Well, I can't say independent matrices, but the matrix represents the transformation. Right? Or independent. Yeah, right. Now, 9 3x3 linearly independent. Make it mathematically precise. Now, one of these 3 matrices, one of these 9 matrices, right, is going to be the identity matrix, possibly multiplied by some phase, right? So it's irrelevant as far as discussion about transformation between different states. Right? One matrix is the unitary, possibly multiplied by phase. So irrelevant. For transformation between states. Okay. The remaining 8 matrices, they form the SU3 group, right? And they can be expressed in terms of 8 independent Hermitian generators, right? TA. What are going to be these 8 matrices eventually? So will end up to be the 8 types of gluons that we have. Right, so 8 matrices that are left, right? They form the SU3 group. And expressed and can be expressed in terms of 8 independent Hermitian generators. Which we call them TA, right? So a general SU3 transformation, general SU3 transformation, right? It's going to be written as U is EIGS now because it's a strong, and then TA chi. Right? Just as a reminder, right? A generator of a group, right, is an element of the group such that when we have a possibly repeated application of the generators on themselves and among each other can produce any element of the group. So basically it's related to the basis. So GS, this is the physics, right? This is the QCD coupling constant, equivalent of the Q. Right. Chi, or chi A, these are the 8 parameters, right, which define the specific rotation that we're interested in. Right. The SU3 space. And TA are the generators, right, the 8 generators, meaning 3 by 3 emission matrices. Right. Now in the U1 case for the QED, we only had 1, so there was no need to introduce any matrices. Right? Now the TAs, just for completeness, right, these are given in terms of what's known the 8 Gelman matrices. So we write down the TA is lambda A over 2, where lambda A are the Gelman matrices. It's 2 N's. Right, that's following Murray-Gell-Mann. I just give them to you, though we're not going to make much of use. The first 3 are just extension of the Pauli matrices. So lambda 1 is just going to be, that's a 0, 1, 1, 0, and then everything else is 0. And then lambda 2 is just 0, minus I 0, and everything else is 0. Lambda 3 is 1, 0, minus 1, and everything else is 0. But then we also have the lambda 4, 0, 0, 1, 0, 0, 0, 1, 0, 0. And then the lambda 5 is 0, 0, minus I, 0, I, and everything else is 0. And then the lambda 6 is 0, 0, 0, 0, 0, and then we have the 0, 1, 1, 0. Lambda 7 is the 0, 0, 0, 0, 0, minus I, 0, I, 0. And the lambda 8 is, oh, that's a surprise, 1 over square root of 3. 1, 0, 0, 0, 1, 0, 0, 0, minus 2. Just that you have it for completeness, because I'm not going to derive them for you right now. There's no real need. Just that you know that they exist. And then the 3 colors can be represented by 3 vectors that are the basis vectors in this 3D vector space, right? That contains this SU3 color representation, the representation of this SU3 color group, right? Basically, this is just to say that R is just 1, 0, 0, G is 0, 1, 0, and B is 0, 0, 1. Right, that's it. Now, the important thing for us is that in exactly similar way to the quantum electrodynamics, right, the Lagrangian is invariant under rotations in the 3D space, right? So the Lagrangian is invariant under rotation in this 3D space. That's the important point. It's identical to what we did in QED. Right, so psi goes to U psi, right, where U was defined here. And the Lagrangian is invariant, right? U is a group element, right? It's a unitary 3 by 3 matrix, which have a determinant of 1, and is presented here. Right?
Out of these 8 matrices, lambda 1, 2, 4, 5, 6, and 7 seem to be a symmetric under exchange of RGB. Lambda 3 and lambda 8 are not, so I guess they're arbitrary. I can rename the columns and rows.
You can rename, yes. You can rename them. That's fine. Okay, so similar to the QED, right, where we use the fact that the U1, unitary 1-by-1 matrices are, we can read them in the form of E, I, Q, chi. We have here exactly the same situation. It's the important thing. So if we look at the Lagrangian, remember what we're up to is a symmetry under the Lagrangian. The Lagrangian symmetric under transformation, right? Local transformation. That's what we had in QED that gives rise to the interactions. So here, the Lagrangian of a free quark right? Psi bar, right, gamma mu d mu minus n psi, right? It's going to transform, right? Psi bar u dagger I gamma mu minus m gamma u d mu. Let's see, there's another typo. U psi. Right. Now the I gamma mu d mu minus m, it commutes with the Gelman matrices because they are constant, right? They're just numbers. So the Lagrangian is invariant under global transformation, right? So since the Gelman matrices commutes SD minus m, Lagrangian is invariant under global transformation.
The commutation with the gamma matrices is because they operate on different spaces.
Commutation is because the Gelman matrices are just numbers, so you don't care. You can move the numbers wherever you want.
Well, that explains commuting through the derivatives.
Okay, yeah, fine. Okay. Now, so the global SU3, that's called the SU3 color. So the global SU3 color symmetry that leads to the conservation of color. Right? This is the QCD charge, essentially. Right? Same as what we did with the QED, there's no point in repeating. What about the local symmetry? That's the more interesting one, right? We want to have the Lagrangian invariant under local symmetry. Namely, the psi, the chi matrices is a function of x of the space. So requirements require the Lagrangian to be invariant under local transformation. Right. So basically, we do exactly what we did with the QED. Right. It's just take the same prescription. It's the nice part. So we first have to replace the derivative with the covariant derivative. Repeat the steps we did in QED. So d mu becomes a covariant derivative, which is just d mu plus some term IGS TA. Then we have a new field, G mu A. Right? And the G mu A, similar to, remember in the QED, we had this A mu. Here we have G mu, and the A goes from 1 to 8, right? These are 8 new vector fields, right? Each corresponding to one of the 8 generators of the SU3 symmetry, right? How do we call these new 8 vector fields? I'm gonna get names physically. Gluons, right? It's gonna be the gluons, right? A is 1 to 8. So G mu A of X, right? These are 8 new vector fields, right? Each corresponding to one of the 8 generators of the SU3 symmetry, right? This will be the vector field of the QCD, gauge bosons. Which are gluons physically. Now there is a small tweak, right? Remember that what we did in QED, right? We introduced this extra field, but then in order to cancel out this extra term, the extra term that we got from the derivative, right, of chi, we wanted the field itself to transform in a certain way, right? So in QED, what we had was that we demanded as a requirement from the field A mu to go to A mu of X, right, under transformation minus d mu. That way we could cancel out the extra term we got from this, the local derivative of chi. Right? Now we have a little bit of a problem because the symmetry group we have, what's the difference between the one we have here and the one we had in the QED? Any suggestion? Actually mentioned it earlier. There is one important difference between what we do here and what we do in QED. What is the difference?
They don't commute.
They don't commute. Very good. The group here is non-abelian, right? So if we make it a transformation, identical transformation, right, to the new field that we got here, right, it's not going to give us a full cancellation of this extra term that we got in the Dirac equation. Right? However, right here, symmetry group is non-abelian. right? The generators do not commute with each other. Right? We got down the Dirac equation, right? I gamma mu d mu plus I g strong g mu a t a psi minus m psi equal to 0. We have this extra commutator which is non-zero. So we must add some extra term to the transformation law of this g mu's, right? So in order to ensure full cancellation of the extra term, one needs to add a term to the transformation law of the field. Right. So again, to make the Lagrangian invariant under this SU3 gauge transformation, then the correct transformation should be G mu A should transform as G mu A minus D mu chi, which is what we had previously. But now we have this extra term, which is G as F A B C chi B G mu C. This is an extra term added to ensure that the Lagrangian is invariant under local SU3 gauge transformation. Now, so chi is this is the local transformation, right? G is the field. F, they have a name. These are known as the structure constants of the SU3 group. So F, A, B, C, they are called the structure constants. Not that important for us. Structure constants of the SU3 group. And they are defined by the commutation relation. They are defined by TA and TB is I, F, A, B, C, T, C. Right, remember T are the half of the Gell-Mann matrices. They put the Gell-Mann matrices, but then I had to have an extra factor of 2. Of course, for abelian group, these are simply 0. But the group here is non-abelian. So the exact values of them are not that important for us. You can simply just follow the math and calculate it. I'll just give you the only non-zero terms. So the only non-zero terms are F1, 2, 3, which is 1, F1, 4, 7, which is F2, 4, 6, which is F2, 5, 7, F3, 4, 5, which is F5, 1, 6, which is F6, 3, 7 is 1/2. F458, which is F678, is square root of 3 over 2. And all the cyclic permutations. All right, so F213 would be a -1. Okay. These are known as the structure constants. You can Google it or Wikipedia it or simply go to the textbook and read it there. And similar to what we did with the QED, if we want to write down the full QCD Lagrangian, then we have to have a kinetic term for the gluons. Right, which will be -1/4 G mu nu A, G mu nu A, which are of course the QCD equivalent of the F mu nu. But we have to be a bit careful because we have this extra term here. Right, so because of this extra term, then when we put down the kinetic term of the, in the Lagrangian, then since we want it to be invariant under the transformation, then the definition of G mu nu must be slightly different than the QED equivalent. So in order to ensure invariance of the Lagrangian, right? The definition of G mu nu must be slightly different than that of the F mu nu. So the G mu nu A is just d nu G nu A minus d nu G mu A. But then we have this extra term minus GS F ABC G mu B G mu C. So I didn't derive the full math of that, but I think you can easily see where it comes from. At least I hope you can easily see where it comes from. Now this addition, right, means that in the kinetic term, right, we have a multiplicity of the form G mu nu, G mu nu, right? So that means that in the kinetic term, right, which we have this one, right, G mu nu, right? We have term, there are terms of the form, like GS squared F A B C F A prime B prime C prime G mu B. I'm forgetting the upper or lower. It says G nu C G mu B prime G mu C prime. Right, we have term of this form. Right. And also we'll have terms, again, this term multiply the last term, multiply one of those terms. So we have terms of the form G, S, F, A, B prime, C prime, and then V mu, G mu A. Gotcha. G mu B prime, G mu C prime. Right. So we're going to have terms of this type.
For the F indices and the G indices that go with it, you keep upper with upper and lower with lower.
Yeah, I wasn't really consistent here. I should have been more consistent. That's because I'm not sure what will be more confusing to put the BC. I mean, if you want to be precise, then yes, I need to put the BC here and the B prime, C prime here, but it's not really, it doesn't really matter because it's not a vectorial or tensorial quantity. They're just structure constants, which are just numbers. So I have the liberation to play with the notation, which is something which is normally completely not allowed. Don't do that in general relativity ever, but here these are just numbers and the notations are not the same, so it's okay. The important here, what?
AB, is there any meaning of A, B, and C being remotely related to covariant and contravariant indices, or is it
just summing over the different possibilities there? No, correlates.
So wherever there are two of them on the same side of the equation, you just sum over it.
No, here you don't sum. The mu and u you're summing. These are just an index, basically.
No, because it's A prime, but for example, in the expression.
No, there's no summation here.
In G mu nu A, isn't there summation?
There is a summation over the mu nu. Sorry. Oh, sorry.
For B and C, right? It must be.
No, you do have a summation. Sorry.
Okay, thanks.
It's a matrix multiplied by a vector. There's no meaning to individual components.
No, you're right. Sorry.
Also, if we're already on the topic, you're using capital G once with mu and nu and once with just mu, but these are not the same thing, right?
I defined here what is G mu nu. This is the definition.
Right. So G mu nu is defined in terms of G mu, which is not this. I mean, it's kind of confused, right? You're using capital G for two different things, right?
Yeah. Like I did not use the same word, right? F, like it's equivalent to this F mu nu, which is D mu A nu. So if you want, you could have used a different letter, but this is the common way it's being written. Right?
Okay, just to make it more confusing. Okay.
All right, so the gauge boson, and F mu nu is a tensor basically, and the same what you have here. G mu is a vector. It's a gauge boson, right? And G mu nu is a tensor, so it's not really. But you're right. It's maybe a bad use of notation, but that's the way it is. It's been done everywhere. I didn't see any textbook that it's not written like that. What is the meaning of these terms? So we have these terms, again, remember the logic, right? The terms are there to ensure that the Lagrangian is invariant under local SU3 gauge transformation. And we have to add this extra term, right? In order to make sure this happens. But what does these terms mean? What do these terms represent?
Nonlinear gluon scatterings.
Exactly. They represent interaction between the gluons and themselves. Right? So this shows that there are four vertices interaction, right? Gluons will be like that. Right, this term. And this term will represent a 3-gluon interaction. So again, one thing that comes out of the theory, and again, you can ask whether, whether we trust this, gauge theory. But I'm just showing you the tremendous success that we have for this theory, because once you accept it, we ended up that the theory actually predicts that as opposed to the photons, which do not interact with themselves, the gluon do interact with themselves, and you can have the 3 gluon vertices and 4 gluon vertices. And again, that follows from the fact that this is a non-abelian gauge theory, right? So the conclusion is that in non-abelian gauge theory, there are interaction terms of the gauge bosons not only with the fermions, but also among themselves. Right? Another way of saying that is that the gauge bosons carry charge, right? They color charge, right? While photons are chargeless, right? They don't carry any electromagnetic charge. The gauge bosons are charged under the interaction. Now, we've already discussed that quite earlier, right? Kind of in one of the introductory lectures, that these interactions are the ones that are responsible for the color confinement and for the fact that we do not see the color force at large distances. So it exactly follows from this theory, just kind of amazing. So what is left is just to write the full QCD Lagrangian, which I basically already wrote, right? So L QCD, right? It's just sum over all the different quarks, right? Psi bar, the quark, I gamma mu, d mu, right? Minus m, psi quark, and then the kinetic term, minus 1/4 g mu a, g mu a. Right, where we had, everything was defined. Right, so this is the g mu nu, okay, and then we have some other transformation, g nu, and we have the covariant derivative. The covariant derivative, there it is. So everything is well defined. Of course, the sum is over the 6 flavors, the quarks. Quite cool, isn't it? So the last comment I want to say is, you know, the quark gluon vertex. Quark gluon. So we have, you know, the interaction term between the fermion and the gluon, right? In exactly the same way as in the QED, it originates from the term I, GS, TA, G, and UA, right? The interaction term is inside the covariant derivative. So we end up with an I sidebar gamma mu R GS TA G mu A psi. So considering the i's, we end up with a minus GS TA sidebar gamma mu psi G mu A just minus J A mu G mu A. So again, we end up with very similar to the QED. We have a form of a conserved fermionic current charged, right, under the strong charge, the A, which is multiplied by a gauge vector. Okay. This is a conserved charged current fermionic. Right, the only fermions involved. And this is the gauge vector. Right. So if we look down at an interaction vertex in the QCD, right? So we have quark, let's say an anti-quark, and they can interact via the gluon, which is denoted this way, right, like spring. This is a Feynman diagram of a quark-gluon interaction. Alrighty. Questions?
This charged current is color charged.
Yeah, of course. Color charge, of course. Current means the color. Color.
So it is also defined without the nonlinear part. You don't count the gluon color in this charge.
The gluon do carry the color, right? This is the A.
I mean, you couple the source, you couple the field to the source current, but the source current is only the external part, it's only the fermionic part.
Yeah, but it is, but they do carry the charge via the matrix TA, right? You have these 8 matrices, right? The gluon do carry current. Remember the psi. Remember I saw that there is a notation. I kind of compactified the notation. There is the R, G, and B. The quarks do carry color.
Wait, the quarks or the gluons? Psi is for the quarks or for the gluons?
Both quarks and gluons.
This psi letter, what does it include?
The psi, R, G, and B, right? Remember, we just put them in a one big notation, right? We had this at the beginning of the lecture, if you recall, right? We wrote down the psi is the psi R, psi G, and psi B.
Okay, but these are still the quarks.
Yeah, these are the quarks.
So does the gluon charge color appear in this current definition?
Here. Right? This is for the fermion, and this is for the gluon, and the G is the gluon.
I guess what I'm thinking is in the analogy to electromagnetism.
Yeah.
J will be the electrons, and G will be the photons.
Correct. Yes.
But now, if the photons also have electric charge, or if the gluons themselves have color charge,
yeah,
should they be added to the J part as well?
No. No, I wrote it down. You're right that I wrote it down in a completely analog way to the way we wrote down for the QED, right? So for the QED, right, we just simply had J mu, A mu, right? And then J mu, right, if you remember, J mu was simply Q and then psi bar, what did we have? Gamma mu psi. Right, that was for the QED. Right, Q is the charge, right, the electric charge. And then we had this interaction, conserved current, psi bar gamma mu psi. Now, note the similarity, right? The thing that is the analog for the charge Q, right, is the coupling constant, right? So the coupling constant here is GS, right? This is the coupling constant with the strong force. That's where all the physics is, really. Everything else is pure math. And then we had the current. But now, since we have a different symmetry group, previously we didn't have to have that because there was a U1 local phase transformation, and this is just a number, right? It's just a phase, which we don't really need here. But here we have 8 different matrices, right? The generators, the Gelman matrices, essentially, or the T mu, which is just lambda over 2. Right? Lambda are the Gelman matrices, and T are the matrices that we're using here. We could just lambda over 2. Right? These are the generators of this SU3 group. So we have 8 different matrices. So we need to specify which one, which is essentially specifying which color we have it. Okay, that's the difference between the QED and the QCD. And since the quarks carry the color, so do the gluons. And that's why we have 8 of them. And because it's Abelian, then these 8 also can interact with each other, which we do not have in QED.
Maybe I'll ask in a slightly different way.
Okay.
If in a situation 1, I have a quark, then my J will just be composed of that quark. If in another situation I have a quark and 100 gluons, will the J be different?
No, the quark carries a color.
But so
you can have two different quarks, right? Think of a proton, right? The proton is made of 3 quarks, U, U, and D. But the U and U are not the same because each one of them is carrying a different color. Right, you can say I have a U green and a U blue.
Okay, so if I have a blue up, that will go in the J.
Yes, if it goes with this is the quark, right? This is everything which is here. Everything here, right? This is This is the fermionic part of the interaction.
So now if I have a blue up quark and around it 100 gluons of different colors,
Yeah.
will they affect the color current, or will they just appear in G?
No, they will appear in G. That just means that this quark will be connected to the blue gluon, basically.
Okay, so J only counts the fermionic sources,
Yes.
even though the bosons are sources themselves.
The gauge bosons.
Yes,
Well, what do you mean by sources? They do carry color.
exactly.
Gauge boson. Well, that means that when they interact, they can transmit the color and they can exchange colors.
Okay.
Okay. More?
I also have a question, a little more general. So everything here is based on the fact that the Lagrangian is invariant over SU3, right? So that was kind of the beginning of everything. And I understand that because you're taking 3 fermionic fields, a single fermionic field is invariant under U1, so you make a vector of 3, you get SU3. But it is still invariant under U1, so you haven't lost the U1 symmetry. You've just added a higher symmetry, right?
I required, well, okay. Yes, I have not lost it, right? Yes, you're right.
So
that is another way of stating that these quarks can also interact electromagnetically.
okay, but that's also an interesting point. But where I was actually going is, how do I know which symmetry to choose? Like there are multiple, right?
Great question. That's when you have supersymmetry. That's that you say, okay, why I'm going to use, right? I showed you the U1, the SU3. I'm going to show you not today, but I think next week, which is going to be the SU. There's SU multiplied by U1. U1 is the unified, the electron. That's a beautiful thing, but that we'll discuss next week, right? So you have U1 and SU2 left, actually. That's also important, right? For the weak, it's only the left, and for the strong, it's an SU3. Again, your question I can only answer in a philosophical way. The standard model describes what we're seeing experimentally, right? We have not seen, and this theory. Remember when they wrote this theory, not all the quarks were detected, right? The theory was written mostly in the 1960s. And the quarks, the idea of the Gallman matrices, etc., the SU3, he wrote it down. They only knew about 3 quarks at the time, the U, D, and S. They didn't know about the others, right? And you get great predictions, right, with this theory. Whether this is a complete theory, likely not. Whether there is a bigger symmetry, maybe the SU5 that people speak of in string theory, maybe. I'm not a string theorist, so I cannot answer. But one thing that I do know for certain is that there is no experimental evidence, again, modulo what we spoke at the beginning of open problems, open problems regarding things such as the nature of dark matter and the nature of dark energy and things of that kind, right? But as far as what we can see in the lab, this theory just gives you excellent predictions and in excellent agreements to everything that has been detected in the lab. So that's why we accept it, right? But that's no different than any other physical theory.
And okay, I understand that. I thought there might be some first principles idea of how to choose the symmetry. You're saying I'll analyze all possible symmetries, and whichever matches the experiment, that's the one I keep, and the others I kind of throw away. Or I call them beyond standard model or whatever.
Yeah, I tend to think that this is what really happens. Whether historically this is the way it worked, I tend to think so, but I'm not 100% sure, so I don't just want to tell you. But you know, Whale came up with this idea in 1929, and people have been developing it since then. And hey, it seems to work, right? You know, in the 1940s and 1950s, there's been many new particles were detected, and so people play around with all types of symmetries, and eventually they came up with this, and you know, it just seems to match. Right, and the beautiful, possibly yet very disturbing fact is that, you know, since this model, the standard model was written in 1970, everything else that's been discovered since then, we talk about 50 years, is been with full agreement with the predictions of this theory. For me, this is quite disturbing. You know, even the Higgs, you know, it was predicted by Peter Higgs back in 1963. It took about 50 years to discover, but you know, it was there. People have expected it. There was no surprise. It would have been much more interesting if there was something surprising that people would come up with. But so far, again, modulo the uncertainties mainly related to measurements in astrophysics, but not so much to measurements we're doing in the lab. The theory is in, you know, just perfect agreement is what we're seeing. All right, more? Okay, let's not waste time, because really I'm feeling that I want to make sure that we have enough time to discuss I told you there are two topics that I would feel really bad of not discussing. So the weak interaction, which we're going to start discussing now, and the Higgs mechanism, just kind of for completeness, just to get the fulfilling. Honestly, I think that we won't have time to fully cover the Higgs because we don't have that many more lectures, but I'll do my best, you know, modulo that I don't want to rush in to make it such that you lose me. I want you to stay tuned, hopefully that everything is clear. By the way, I told you last time, and I remind you again, I got the notification. You have right now the students' feedback is welcome. You can write down your opinion on this course, and it's very welcome. Everything you have to write, please write. If you like it, please write it. If there are things you think needs to improve, please write it down. It's important. It's important. It will be useful. Possibly not for you, but for the future generations of students. So in the long run, everybody benefits. Okay, so we spoke about the QED, we spoke about the QCD. Now I'm going to speak about the weak interaction. So arguably, the weak interaction is the most interesting one because it has several features which are unique. You know, the QED, the electromagnetic interaction, and the strong interaction, they're essentially very similar to each other, right? There's a difference in the symmetry group that they obey, but the structure is the same, and the predictions are the same. But the weak interaction has several unique features which discriminate it from both the electromagnetic and strong. So for example, when, you know, we have had a tutorial at least in the weak interaction. So there will be parts that I go briefly because we already covered, but I want to emphasize a few parts to give them a more global picture. So remember in the weak interaction, we had the neutral current and the charge current. So I want to focus on the charge current weak interaction. Charge current. For short, it's going to be CC, weak interaction. Yeah. I hate it when I do weak interaction. So remember, it is that there are a few unique features. It is mediated by the W plus minus bosons, which are massive. they are charged. So first they are massive, right? So as opposed to the photon and the gluon, which are massless, they do have mass. Again, we'll discuss, I hope we have enough time to discuss the Higgs mechanism on how they get the mass. They are charged. Which means that they couple together fermions which differ by 1 unit of electric charge, right? And another experimental fact is that this is the only place in the standard model where the parity is not conserved. Both the electromagnetic and the strong interaction do conserve parity, which means that when we look at the process, we cannot tell if we look at it directly or we look through a mirror. Well, 3 mirrors, right, in each direction. Here we can. This is an experimental fact, right? It is the only place in the standard model where parity is not conserved, right? So one thing that discriminates weak interaction with other interactions is that this is the only interaction that involves neutrinos, right? Neutrinos are not participating in neither the strong or the electromagnetic interaction, only in the weak interaction. So neutrinos only participate in the weak interaction, right? For example, right, if we have a decay which involves neutrinos, right, then we know it is a charge current weak interaction process. Right? Charge current weak interaction process. Right. So any other decay that involves neutrinos, right? So if you have other examples, right? So the ion decay into muon plus neutrino. The kaon decay into muon, not a muon, it's muon plus antineutrino. These are all weak. Now, kaons, in fact, that were detected, they can be decaying without neutrinos. They can be decay. So kaon, we have that decays into pi minus plus pi 0. That can happen. Right, this is a hadronic decay. Of kaon. There's only quarks. Right. So that means that when we see it in the lab, that means that it can, in principle, be due to the strong force, right? But it is, in fact, a weak process on the quark. So is it a strong force decay or weak? So the answer is this is a weak interaction. And the way to discriminate is there are two things. One is that the rate, right? The strong force happens to be much faster than the weak, right? And the weak interaction tends to be much slower. So strong interactions are much faster. just that you get the feeling, right? The lifetime of the kaon is considered to be quite long, which is 12 nanoseconds. Our count is about 12 nanoseconds, that's long, relative to other particles. And also, if the decay was via the strong force, that means that it would nearly never decay into the muon, an anti-neutrino muon, right? Because it will be much faster decay to the hadrons. But the branching ratio is about 64%, right? So chi minus muon plus neutrino muon, okay, minus 24 minus 0, about 64 over total. Right. Everything else is 64%. That's quite long. So it's quite a lot, which means that a lot of the times the kaon do decay into neutrinos, which we know must involve the weak interaction. And the other thing is that this process changes strangeness, because the kaon is the up or and the strange, and strangeness is conserved in strong interaction. Right? The decay of the kaon and the process conserves changes. Strangeness. Is conserved in strong interaction. Now, one thing which we discussed already, so let me repeat this quickly, is the effect of quark mixing. So quark mixing. So the basic vertex of the charge current weak interaction, right, would go something like that. We have a lepton, then a weak, then a W minus, right, and then neutrino. Or you can have quark, which would end up with a W minus and then up type quark. Right, this is the basic vertex. The basic vertex of charge current weak interaction. That's how it looks like. But now, when we look experimentally, so when we look at the leptons, we see that there is always a conservation of leptonic flavor. There is never a mixing of leptonic generations. There is a conservation of leptonic flavor. Means there is no mixing of leptonic generations. And we see that all the coupling constants that are associated with the vertex, right, are the same for all the three lepton families. The coupling constant associated with the vertex is the same for all three families. Which means that we can organize that into doublets, right? So we can organize them Right, neutrino EE, neutrino mu mu, and neutrino tau tau. Right, so this is for doublets. Right, which means that the interaction connects only particles that belong to the same doublet. Right, the charge current weak interaction connects only particles that belong to the same doublet. I mean, this is a fact, right? Which means that if we look at the 2D space, right, it will represent a diagonal matrix. Right? An electron can couple via the weak interaction only to neutrino electron, but not to a neutrino muon or neutrino tau. This is for the left diagram. This is for diagram A. Diagram B. A. But now if we go to diagram B, the one that involves the quarks, then we're seeing a different situation. Again, this is all experimental facts. So one key difference is that we already spoke, is that quark flavor is not necessarily conserved, right? Generations can be mixed. It's not always conserved. Generations can be mixed. Again, it's an experimental fact. A strange quark can decay into a down quark, an up quark. Yeah, the W has to be the up quark. Right? And we also discussed that the coupling constant is not always the same, right? It does depend on the flavors of the quarks involved. Right. Now, one of the great discoveries, right, is the fact that despite the seemingly lack of universality, right, it turns out that you don't have to abandon this doublet representation, right? But there is a universality, just we have to change the basis, right? So it's not, this is called the mass basis. These are the ones that we're measuring their masses, right? So we just have to change, this is the mass basis is what appears in the Hamiltonian, right? But if we change the basis, we can have a new, we can stick with this doublet representation. So it turns out, right, it was discovered, this is exactly what Kabibo did. We can keep the universality by changing the basis right from the mass basis right to the Hamiltonian of the quarks right to what is known as the weak interaction basis. Which means that we can arrange the quarks in different doublets than we arrange the leptons, right? so it means we arrange the quarks right as right in the interaction basis, right? Right. Rather than up and down, we have mu d prime, ds prime, and t d prime, right? Where d prime, s prime, and b prime, right, is a linear combination of d, b, and s. Now, it's a notation, right? But I don't really have to do it for the up ones, right? But anyway, the charge coupled weak interaction always connects an up type quark to a down type quark. So the choice to modify the basis of the down quarks is just, so just a convention. You could easily do it for the up quark. Right, so the basic vertex for the charge coupled interaction of quarks look the same. This would be the d prime, s prime, and b prime, u, s, e, and t. As I said, the one that came with this idea first was Nicola Cabibbo. That was in 1963. So now the nice thing is that at the time there were only 3 flavors of quark which were known. It was only the U, D, and S. That's it. And his problem was to explain why is the count decaying into muon and antineutrino, right? And this is a very rare event. Right? It's approximately 20 times less than what was expected, given that the known rate of the pion decay. Cabibbo, right, motivation, there was the count decay to the rate that is about pion mu is about 1 in 20. Right? But of course the Feynman diagram looks exactly the same. D or S if it's a count, right? And, anti-up. Change here the weak interaction becomes an anti-neutrino and the left one. Now at the time in the 1960s, Cabibbo knew only about 3 types of quarks, just the up, down, and S. I didn't know that this whole structure of 6 quarks was unknown back then. Right, so the decay, pion, or count. So his idea, which we already discussed, was to connect, propose a connection between the weak eigenstates and the mass eigenstates, right? Which was given by some orthogonal transformation, which was represented by a unitary matrix. So Cabibbo suggested, right, D prime and S prime are connected to the DNS eigenstates, right, by the Cabibbo matrix, cosine theta Cabibbo, sine theta Cabibbo, minus sine theta Cabibbo, cosine theta Cabibbo. Now, if you do that, you end up at the Feynman diagram look exactly the same. Now, I know I'm running a little bit out of time. I just want to finish that part. Right, so for the pion decay, right, and for the count decay, right, they look the same. The difference is that just assume that the coupling constant here is g cosine theta, and here would be g sine theta. Again, the quarks that make base, right? So DNS, yeah, let me write it down because just to avoid confusion. I'm sorry, I'm taking a few more minutes of your time. So the quarks that make the hadrons are in the mass basis, right? This is the DNS quarks, right? Now, the interaction, right? Since they have to interact with the up quark, right? Then they're first projected into a D prime state, right? And that gives the amplitude of the sine theta and cosine theta, right? They interact with the up quark, first projected to the D prime state, right? This is the interaction basis, and gain a factor, amplitude gain a factor, right? Cosine theta can be both, and sine theta can be both. And the coupling constant is the same. It means that it's clear that the branching ratio, right? Branching ratio of the count, mu minus plus inner mu, divided by the branching ratio of the pion, decay into mu plus mu, right? Is proportional to tangents squared of vacancy. Just by looking at these processes, right, so the pion decay, whatever, the count decay. I'm not saying to the muon, but I wrote down generally. So for experiments, then theta Kabibo is about 13 degrees. Sorry, 0.13. Nicely, he was able to predict the decay rate of the other strange baryon, such as the lambda baryon. The lambda baryon is a UDNS. So Kabibo predicted the decay rate and decay rate of other strange baryons. The lambda 0, proton plus electron plus neutrino. Lambda 0 is just a UDS. Now, this was later extended, as we discussed, by Kobayashi and Moskawa to the 3 generations. Remember, at the time that Kabiba wrote this, there was no, we knew only about 3 quarks. So processes that their amplitude is proportional to sine theta, they are Kabiba suppressed, and the others are Kabiba favored. And this would be a Kabiba favored. Kabiba favored. This would be a Kabiba suppressed. Then it was later on generalized in 3 states by the CPM. And 2 of those, Kobayashi and Mastawa, got the Nobel Prize for it. All right, I think I ran too much out of time, but I was trying to speed up so that we make sure that we have enough time to cover the week, which has several very interesting features, as well as the Higgs. Any questions before we go home? Any questions? So I'm quite happy that despite my initial expectations, we ended up without any technical issues. That was not clear to me 2 hours ago, but that's good. Any questions or comments before we leave? No, that means that everything is clear. Maybe, but just make sure that this is really the case. All right?
Okay.
So, in that case, have a nice rest of the day.